Okay, note to self, disable the entry tones when I set up the next meeting. Play a chime for raised hands. Yeah, I was really disappointed when UC abandoned WebEx and went to Zoom because I had spent the years 2020 and 2021 getting to know all the ins and outs of WebEx, and then I had to learn something new. And when you're as old as I am, learning something new sucks. I'm uh, I'm resistant to change, most change. I do change my shirt once in a while. I do change my pants occasionally. That's about it, though. All right, we currently have me plus 4. We lost one person. Somebody withdrew since Tuesday, so we are now 7 students. Probably because I used the words linear and algebra in close proximity to each other. That scares a lot of people. I tried to get Dr. To advertise this class around the state, so like students at OSU and Ohio Northern could log in and take it, but I don't think he took me seriously when I did that. So next time, I think I'll make a more concerted effort, perhaps, to try and get to get that going. It would be a good class, I think, for a remote class because obviously everything's remote. It's well suited for that as well. All right, let's get started. It is Thursday, August 24th, and I have 12:31 on my Swatch watch, so let's get going. As a reminder, here's the schedule for the rest of this week. And nobody showed up at office hours this morning. That's not surprising, though, given the first week of class. So I don't have anything listed tomorrow, but I'll be on campus. I'll get to campus around 8:30 or 9, and I'll be there until probably 2 or 3 o'clock. I have a class in the morning, and I have a conference call at 1. I'll probably go to lunch right after my 10 o'clock class. But if you need to reach out to me, I'm there tomorrow. I haven't posted office hours for next week. They won't be on Monday. Probably it'll be on Wednesday and Thursday again, but I'm just not sure. I'll post those to Canvas when we get to Sunday afternoon or Monday morning. All right, we still don't have a teaching assistant for the class, which is problematic on a few different levels. It's kind of annoying that we have to wait, but that seems like every year now there's this, or every semester now there's this haggling that goes on between the department and the college for funds that are used to pay for teaching assistants, and it seems like we always have to wait till the end of the first week or into the second week. Anyways, we'll get that wrapped up hopefully by next week, and then we can finalize our syllabus. I did post homework number 1. That's online now, and you can find that if we, let me go ahead and launch a browser, and I can show you where that information is. You guys are probably better at using Canvas than I am at this point. There we go, Canvas, it'll want me to log in. I've got one of my sons in the basement playing video games today. I can hear him yelling every once in a while. He's so I'm going to be competing with him for bandwidth today. Hopefully it won't be an issue. Usually isn't. So right, so if you go here to homework assignments and solutions, then you can see homework number 1 is there. And if you click on that, you should see something like this. You download a PDF that gives you the problems, and then here is an Excel template that I'd like you to use for some of those problems. So I listed that as being due next Thursday, 1 week from today at 11:59 p.m. So if you guys, we can work through some examples either late today or in class on Tuesday, doing some matrix operations with Excel, but I imagine most of you have done it or can figure it out pretty easily. And then what you'll see here is once we get the homework turned in, I'll post a solution. I'll post both a PDF and an XLS file in this case. And then homework number 2 has some beam modeling in it. And when I post a solution to that, I'll post the the SAP database file and the visual analysis project file as well. So that's why I have this set up as a table like it is. So, right. Okay. Hopefully you guys have also checked on our handouts page or our content page. I've got 3 PDFs here. The first one is this PowerPoint presentation. And then the second and the third one are a tutorial that we'll work through today, both in visual analysis and SAP 2000. So let's see. That begs a question, actually. Why do I work in 2 packages instead of just choosing one? And the answer to that question is that because I see value in using more than one package, and I've been told that pedagogically speaking, from an educational point of view, that there's value in teaching with more than one application. So our engineering education faculty, I know you guys probably love them from your experience in the ENED courses, if you were an undergraduate here at UC. They preach the mantra that if you learn how to program or write code in more than one language, that you become a better programmer. And that makes sense to me. I'm not sure that I buy into it as much as they do, but certainly understanding how to create a structural analysis model in 2 different packages would probably lend to a deeper understanding of what's going on behind the scenes. And that's ultimately my goal in the class, is to give you that understanding. So for some of the stuff that we do in the class, most of the earlier stuff, we'll do it in both visual analysis and SAP 2000. After we get a few weeks in, we'll probably use visual analysis less and less. I'd mentioned on Tuesday that visual analysis has the advantage of being easier to use, but SAP has the advantage of being a fundamentally more useful program. It's just better in a lot of ways. All right, so that being said, let me go back to the PowerPoint. What we're going to do is we're going to focus on modeling a bridge girder. And so this is kind of an interesting subject. Has any of you had bridge? I don't think any of you have had bridge engineering. Have you? Maybe Sujin, you might know. Okay, so anyways, there's a whole lot of bridge engineering knowledge that goes into this. And, we have a bridge system. How are we going to do the analysis? So my goal here is to present this in a context, but then just give you a very narrow view of what's going on. So it's not a course on bridge engineering, but if you were a bridge engineer, here's how you could use visual analysis for SAP 2000 to get the results that you would need to do a design of a bridge girder, to do an analysis of a bridge. So this is a sheet from one of ODOT's old standard drawings. And if we look at the lower right, I think you'd see that it's prepared back in the 1980s. It was, well, actually, it was originally, it was revised in March of '58. And then it was revised again in '59. And then I think there's some stamps on here that say, maybe it's '56. That's hard to read. So these are old drawings, but to provide some context, when the interstate system went into place, I-75, I-71, et cetera, they had a ton of grade separations that they needed to design. Basically, you have a country road that's going to be intersecting with the interstate. You can't put an intersection there. You can't put a roundabout there. So you have to provide a grade separation. You either need to build a bridge over the country road, or you need to build a bridge over the interstate. So rather than designing each one of these bridges individually, what the DOTs did is they went in and they came up with a table of standard designs. So what you see here is this enormous table that gives you different rolled sections that you would use as bridge girders, depending on the span lengths that you wanted, depending on the roadway widths that you needed. And so a contractor could go in and bid a job just based on typical drawings for bridges. And then that made the process of constructing all these grade separations a lot more efficient. So the one that we're going to narrow in on is an example that I use in bridge engineering. I call it the Indian River Bridge, just to give it a name. It's a fictitious bridge. It probably exists someplace, but in the context of my class, it's just a fictitious hypothetical bridge. I call it the Indian River Bridge just to give it a name, so that when I talk about it, I'm not saying, oh, it's that bridge with 60, 75, and 60. So yeah. And probably if I were to name it again now, in order to be PC, and I would probably avoid the word, the I word. But I'm going to go ahead and ride that train until it crashes. So here's if you look at the upper right part of that drawing, this is a typical structural layout. So each of these bridges has 4 girders. They have 2 intermediate piers. So here's an intermediate pier. I guess I could draw on this. Here's an intermediate pier right here. Here's an intermediate pier right here. This is an abutment, and this is an abutment as well. In this context, we could refer to it as the left abutment and the right abutment. But typically what you would do is you would stand at the west end of the bridge and look east, or you would stand at the south end of the bridge and look north. And in that case, the abutment that you're standing on is the rear abutment, and the abutment at the opposite end of the bridge would be the forward abutment. Maybe a little bit more bridge knowledge than you really need. If we go and take a look at some of these dimensions, right, we have span lengths up here that we need to know. We have girder spacings that we need to know, right? Those are all called out in that table. So if we zoom in there, we're going to have a middle span of 75 feet, 2 end spans of 60 feet. It's going to be a 36 wide flange 230. Which is slightly different than a W36 by 230. That's an old version of the manual. That's not really germane to this conversation. I keep diving in too deep into the details. One other thing that's noteworthy here is that there are moment plates, and what those are reinforcing plates for the girders where the moment is the heaviest. So the moment tends to be heaviest over the piers in the negative moment region. So in order to reinforce the girder, we put in, we call them cover plates. Nowadays, they call them moment plates back then. And then you see the number of cross frames, et cetera, et cetera. So this gives us all the details that we would need for our bridge. So if we look at a cross section, this is a half section. So this is a line of symmetry here. So you can see how this is all spaced out. So what we have is girder 1, girder 2, girder 3 would be over here, then girder 4. And so what we're going to do is we're basically going to model one girder in this bridge, and then we're going to subject the loads for the bridge onto that one girder. Now this drawing here is only a half section of the bridge, and it's really busy with all the call outs and the language. So what I'll do is I'll go here and I'll say, let's use this. And I know the guardrails are different, but I had this already drawn to save me some time. So let's use this as an example. So when we put loads on this thing, what we end up doing most of the time is we take a tributary width for all of the gravity loads. So if we're going to model this girder here, let's say we're going to model girder number 2, what we would do is come over and take a tributary width that goes halfway to the girder to the left, a tributary width that goes halfway to the girder to the right, and we would include the self-weight of that steel girder plus the self-weight of the concrete that's within that tributary width. That's probably common knowledge to everybody in this room. What's probably not common is how we apply the lane loads or the truck loads on this bridge. So what we would do in bridge engineering is we would come in and we would say, all right, all my lanes are 12 feet wide. So I'm going to come in here and say, well, gee, the lanes look like that. So I might have lane 1 here, I might have a lane 2 here, and a lane 3 here. And then what you do is you come in and say, all right, I've got my highway truck. It's an HS20 or an HL93 or whatever truck you're designing for. I'm going to put this truck over here in this lane as close to that girder as I can get it. I'm going to put this truck over here in this lane as close to that as I can get it. And so what we end up doing is we take a truck load that looks like this with 3 axles. We spin it sideways and we come up with something that's called a distribution factor. And so the distribution factor in the context of bridge engineering is equal to the number of lanes worth of loading that go on a girder. And so I'm showing 2 lanes worth of loading here, loading from lane 1, loading from lane 2, but part of that load is carried by girder 1, part of that load is carried by girder 2, and some of it is carried by girder 3. So what we can do is go through an analysis, and we might say that the reaction force on the deck due to girder 2 is equal to 80% of 1 lane's worth of loading. And so we use that distribution factor when we apply the live load. So with that being said, let's go ahead and start modeling one of these girders. And this is going to be I'm just going to work along on visual analysis first, and then you guys can come along and you can either try and work along with me, or you can just sit back and watch, whatever works for you. What I'm going to do, though, is I'm probably going to work fast for you. So if you have a question, go ahead and raise your hand. But if you get behind, realize that you can always come back and check out the recording of this tutorial after I post it on YouTube. I posted Tuesday's recording today, and I'll probably try and post today's recording this afternoon in case you guys fall behind a little bit on this. So I'm going to go to my other computer, which just runs a little bit better. I need to enable sharing. How do I do that? All participants. Okay. These are little quirks that I'll get better as I go on. All right, so I'm going to share that window. All right, so what you should be seeing is my visual analysis window. All right, has anybody taken the time? I'm still projecting my sound and my video through the Surface, but now I'm sharing the screen on my Precision. All right, did anybody take the time to look at any of the IES tutorials or anything online? Probably not. It's a busy week for you guys. I know that. So, all right. So this is the main window for visual analysis, so there's a few things that you should be familiar with. This is the main workspace right here. This gridded area. I like that. That's nice. It's looks like quad paper, so it makes me feel all warm and fuzzy inside. There's a tool down here at the bottom that will give us information about objects that we select. Over here on the left, we have something called the Project Manager, and it's a very rich dialog box. There's several tabs. Each tab has a lot of different things. You can minimize them, and it's context sensitive. So if you click on a member, then you get one thing. If you click on a node, you get another thing. And so if you click on nothing, you get something else. So that dialog box is very rich. It's very dynamic. And then up here, you have the ribbon, of course, that you're probably familiar with from working with the Office products. All right, so let's see. I've got two different versions right here. Is the visual analysis version. So the problem statement says we have a W36 by 231 that's used as a girder in the Indian River Bridge. The girders are arranged as 3-span continuous beams with spans of 60, 75, and 60. We have an interior girder subjected to a dead load of 1,450 pounds per linear foot. We want to construct a model of a single girder in visual analysis and use that to plot shear force and bending moment diagrams, report the maximum and minimum shear force and bending moments, and then determine the maximum deflection in each of the 3 spans. Right, so fairly common problem. This particular one doesn't have any live loads in it, but then there's a second one that I'll post when we get there that we'll go back and model some live loads. All right, it occurs to me that I haven't finished the introductory modeling presentation, so I should probably do that. Let me go ahead and launch that, and since I'm working over here, I'll just launch it over here. That's M1, right? And I'll move that over there, hit F5. Nope, let me hit Shift F5. We had talked about different types of modeling, BIM models, Navisworks, that type of thing. And we stopped, I think, when we were on this slide here. So picking up at this point, this is where we talk about the basic approach that we use to modeling structures. And so here's a truss that I use as an example. It looks rather small, and it is. It has what, 1, 2, 3, 4, 5 joints, 1, 2, 3, 4, 5, 6, 7 members. So it's not a large truss. But I use this as an example when we start doing the matrix analysis. And as a first problem, it's a big problem. So you get a matrix that is 10 by 10 that you have to invert. And anyways, so the basic approach that we use for modeling these structures is that we replace each of the physical members in the structure with a line object or an element, and each of those objects or elements is connected to each other using a node. So what you see there is in black the actual depiction of the truss, and then each of the red lines represents a line object or an element, and each of the blue dots represents a node or a joint. And so that's basically what we're going to do when we go through and model these structures is we're replacing the physical members with hypothetical or analytical objects. Now, the terminology here gets a little bit cumbersome. I'm using the word object, I'm using the word element. In a lot of cases, those two things are synonymous with each other, but in some cases they are not. SAP 2000, for example, distinguishes between an object and an element. The word node, the word joint, those are usually synonymous in all cases. So basically, we have some rules that we follow, and those are here. Every member is modeled by an element. Every element connects two nodes, one at each end. Every node has degrees of freedom that define the motion, and a rigid body motion is not permitted. It's mathematically unacceptable. So I'm actually going to switch back to the other computer. I apologize for the, I want to be able to sketch on this, and in order to do that, I need to be on the other computer. I apologize for the discontinuity here, but I think it'll make better overall. Let's go back. I want to share that screen. There we go. All right, so every member is modeled by an element. Every element is connected at the nodes. So one of the things that you can't do is, in general, you can't cross over a node. So note that this bottom chord of this truss here is modeled by one element there and another element there, one object to the left, one object to the right. If you were to come in and draw one element that spanned like that, that's bad form. That's unacceptable unless you make some special accommodations. That will give you an error in the model. So you have to have one element that goes from the node at the bottom left to the node at the bottom of the middle, and then another element that goes from the bottom middle to the bottom right. In fact, the way I've drawn it there with the element shrunk a little bit, that's actually a feature in most of these packages that lets you draw with shrink turned on so that you can see where each of your elements terminates. Now, up here at the top, you see this says discrete element models. And the reason that I include the word discrete is because there's one element representing each of the physical members in the structure. If we were to go on and use more than one element, then technically it becomes a finite element model like this, or a finite element model that looks like this. And so those are not discrete element models. Those are continuum models where you have more than one element representing each of the physical objects in the model. So that is one distinction. If you went to Dr. Rosati and asked him what his distinction was, he'd probably give you something similar, but maybe a little bit different. All right, so here are the rules again. Every node has degrees of freedom that define motion as well. So what is a degree of freedom? Basically, a degree of freedom is an expected motion associated with an object. And so the motion that we deal with is either a translation, a delta x, a delta y, a delta z, or it's a rotation, a theta x, a theta y, or a theta z. So depending on what type of structure we're modeling, we have different degrees of freedom associated with each of the nodes in our model. So if we were modeling a two-dimensional truss in the xy plane, the degrees of freedom at each node would be displacements in the x direction and in the y direction. We would have a delta x and a delta y at each one of the nodes. And so since this is probably modeled as a truss, let's go back here and draw in those degrees of freedom. So let me use blue for that. I don't know why, I just always use blue. So this would be delta x, this would be delta y, so that node would have 2 degrees of freedom. Up here we would have delta x, back here we would have delta y. And so at each of these 5 nodes, we would have 2 degrees of freedom. So we would have a total of 10 degrees of freedom for this small truss. Like that and like that. Now, we don't worry about rotational degrees of freedom in a truss because the assumption in a truss is that every member is pinned to the node. And so if the member is pinned at the node, then the node isn't going to rotate at all. It's free of rotation. So there's only 2 degrees of freedom, displacement x, displacement y. All right, now let me go back to the slide at hand. That's actually a touch screen. That'll save me half a second. There we go. So if we look at a 2D frame in the XY plane, then we retain the two displacements, delta x, delta y, but we also add a rotation about an axis that's parallel to the z-axis. So we have 3 degrees of freedom in every node. We have delta x, delta y, and theta z. If we look at a 3-dimensional truss, then we have 3 displacement degrees of freedom, delta x, delta y, delta z. And if we look at a 3D frame, we have 3 displacements and 3 rotations. We end up with delta x, delta y, delta z, theta x, theta y, and theta z. So it works out that when we construct a model of a structure like this, we're actually solving a problem that looks like this. We have a stiffness matrix multiplied by a displacement matrix that is equal to the loads. It's like a spring problem in physics, right? You have a spring stiffness K, you have some displacement, and then you have the resulting force in the spring. Except in this case, it's presented as a matrix in a matrix format instead. So you have a matrix K, you have a vector of displacements, and you have a vector of loads like that. And so the size of that matrix K is the number of degrees of freedom by the number of degrees of freedom. So if you take that truss with 5 nodes, each node has 2 degrees of freedom, you end up with a stiffness matrix that's 10 by 10. It has 100 elements in it. Some of those elements are going to be 0. In fact, a lot of the elements are going to be 0, but it's still a 10 by 10 matrix. So you can see that when we present a small problem, it gets rather large mathematically before rather quickly. Anyways, so that's in the context of a 2D truss, a 2D frame, a 3D truss, and a 3D frame. So one of the things that is interesting, let's see, yeah, okay, I want to see where I'm at here. So when we look at those degrees of freedom, we're going to be looking at, say, for a 2-dimensional frame, I typically draw the nodes as boxes when it's a frame. And the reason why, so if we have a truss, I'll draw the node as a circle like that. If I have, let me make that a little bit bigger, I guess, since you guys might be, is anybody actually working on their phone? Probably not. So then there's a box. If it's a truss, I usually draw the node as a circle. If it's a frame, I draw the node as a box. And the reason why is that when we go in and look at the truss, we're only looking at displacements in 2 directions. When we're looking at the frame, we're looking at a rotation as well. And that box is meant to imply that there is a rotational degree of freedom there, because you can see a box when it spins, but if it's a dot, you can't tell when it spins because it has no corners, right? So in this case, we would have a delta x, we would have a delta y, and a theta z. I call it theta z. It's theta about an axis parallel to the z-axis, right? Within that context. So, right, if we go in and look at this, we end up with 5 members. We have 7 different elements. And so what we would do is we would go in and number our degrees of freedom like this. So we would have degrees of freedom 1 and 2 at node 1, 3 and 4 at node 2, 5 and 6 at node 3, 7 and 8 at node 4, and 9 and 10 at node 5. And the numbering sequence that I use is rather anal retentive, but it makes a lot of sense, especially if you're one of the few people on Earth that likes to write code. Then this will make a lot of sense to you. So we have the ith node number, and we could define the degree of freedom based on the node number. So if we go in here, for example, and we look at node number 2, so we could say that delta x at node number 2, that degree of freedom is equal to 2 times the node number 2 minus 1, so that's equal to the 3rd degree of freedom. If we go in and look at delta y, at node number 4, for example, then delta y has a degree of freedom of 2 times the node number, that's 4, and then that's equal to 8. So that's the 8th degree of freedom. So you could go through here and you could say any degree of freedom that has an odd number is going to be a displacement in the x direction. Any degree of freedom that is an even number is going to be a displacement in the y direction. All right, so we can apply the same idea to this, which is obviously a frame. So my analytical model for this frame is going to look like this, where I have those nodes represented by little boxes because they now have rotational degrees of freedom. And then what we would do is we would come in and identify the degrees of freedom for this frame like this, right? And the numbering sequence that we're using is shown here. where delta x at any one node is defined as degree of freedom 3 times the node number minus 2. The displacement delta y at any node is defined as 3 times the node number minus 1, and the rotational degree of freedom at any node is defined as 3 times the node number. So if we go, for example, we look up here at this degree of freedom, so that is a delta y. The degree of freedom number is going to be 3 times the node number, that's node number 3, minus 1, so that's going to be 9 minus 1, or degree of freedom number 8. We can come over here and we could say for this rotational degree of freedom, that degree of freedom is theta about the z-axis. So we say that's 3 times the node number, which is 5, or that's the 15th degree of freedom, right? So then you could go through here and say that you can identify the degrees of freedom by their number. So the first degree of freedom at any node is delta x, the second degree of freedom at any node is delta y, and the third degree of freedom is theta z. All right, so go ahead.
Why do we have a rotational degree of freedom at the pin center support at the bottom?
That's a good question. And the reason why is because of the formulation that goes into the element. It has to be there, even though it's not restrained. There has to be a rotational degree of freedom at that point. And so what Joe is saying is, if we go back to this slide here, where there's actually a pin support, this node is free to rotate. So it has to have a rotational degree of freedom. And when it rotates, it's going to create, well, that wasn't the best. It's going to create bending in that beam. And in order to get the bending moment that results from the rotation of that node, there has to be a quantifiable rotation at that node. So there can be a quantifiable rotation at the end of the member that's connected to the node. If we didn't have that in there, if that was a truss node instead, then that beam wouldn't pick up any moment at its end. And it can't anyways, but analytically speaking, it has to be there in order to capture that. All right, so when you go through and use a program like Visual Analysis or SAP 2000, you don't need to identify the degrees of freedom. It's going to do that for you, and it's going to use a process that's very similar to the one that I've just outlined here. But I think that it goes a long way to understanding the operation of the program, to understand what's going on behind the scenes. So one of the first homework problems is for you to go into a truss and identify the degrees of freedom, and then calculate some of the connectivity of the members in that truss, and then calculate some directional cosines. And it might not be obvious now why we're doing that, but kind of like Mr. Miyagi telling Daniel-san to go wax the car, eventually you'll see the utility of calculating directional cosines and connectivity. Now, one thing I'll bear in mind, it bears mentioning at this point is that when we go into Visual Analysis in SAP 2000, the coordinate systems that they use as a default are different from each other. So when we go into Visual Analysis, it assumes that the XY axis is in the plane of the Earth, and I said that backwards. It assumes that the XZ plane is the plane of the Earth, and the Y axis is vertical. So the Y axis is the gravity axis. So when it applies gravity loads by default, they're applied in the negative Y direction. SAP 2000 makes a different assumption. It assumes that the XY plane is in the plane of the Earth, and that the Z axis is perpendicular to that. So when it applies gravity loads, those gravity loads are in the negative Z direction. So if we come over here and do a little bit of sketching, that would make this a sketchy chart. Then let's see, this is going to be the Y-axis for Visual Analysis, like this. And so if that's the Y-axis, then this is the X-axis, and that's the Z-axis, and that gives us a right-hand coordinate system. So when we go in and do the same thing for SAP 2000, then what we have is the X-axis defined here, the Y-axis defined there, and the Z-axis defined there. So when we go in and apply a gravity load, that gravity load is applied in the negative Y direction for Visual Analysis, and it's applied in the negative Z direction for SAP 2000. Whoops, that's the wrong shade of blue. That's unacceptable. There, and that's much better. Okay. And so when we go in and do a two-dimensional model within the three-dimensional space, a lot of times what we'll do is we'll work in the XZ plane for SAP 2000, and by default over here, we're going to work in the XY plane for visual analysis. And so that's a little clunky. It creates a lot of confusion. So by calling it out here, you know what to expect. Now that you know what to expect, hopefully you guys will all make fewer mistakes. You're going to make mistakes. I still screw that up from time to time, but yeah. All right, so the next topic on this presentation is the distinction between restraints, constraints, and releases. And so these are three different things that occur in models with regularity. And these terms are very specific and very important. There's a lot of things that I say that mean the same thing, you know, like a node and a joint, those are kind of the same thing. For a lot of cases, an object and an element are the same thing. But if you say restraint and you mean release, that means two very different things. If you say constraint and you mean restraint, that means two very different things. So I want to define them up front, and then I'll reinforce that as we go through the course. So a joint restraint creates a relationship between some degree of freedom and an absolute reference frame. Now that sounds very analytical, but let me illustrate that by going back here. So if we look at the nodes at the bottom of this, these are going to be nodes that have restraints. So if we come in here and look at nodes 1, 4, and 6, and we look at the degrees of freedom, that means that node number 1, degree of freedom number 1 is going to be restrained, degree of freedom number 2 is going to be restrained, and degree of freedom number 3 is going to be restrained. Over here, degree of freedom 10, degree of freedom 11, those are both restrained, but degree of freedom 12 is not. At the right, degree of freedom 16, 17, and 18 are all restrained. Now, when I use the mathematical definition and say it's a relationship between a degree of freedom and an absolute reference frame, that absolute reference frame is that those degrees of freedom are equal to 0, right? We're saying that that node is fixed. It's not going to move. So we know delta x at node number 1 is equal to 0. Thus, delta 1 is equal to 0, delta 2 is equal to 0, theta 3 is equal to 0. So it's very specific. It creates a relationship between the node and an absolute something, all right? Okay, let's go back to that definition. Now, the next thing is a constraint. A joint constraint creates a relationship between a degree of freedom at two different nodes. So you're creating a relationship between two different degrees of freedom, or maybe more than two different degrees of freedom. You're not creating a relationship between a degree of freedom and an absolute reference frame. So let me go back to that frame again. Go here. And so one of the common things that we would do in our models is we would come in and say that, boy, I wish I had gray. I don't have gray. I'll use green. There's probably a floor slab up here on this level, or maybe it's a roof slab. So we would probably model that as a rigid diaphragm. And what that means is that if it's concrete, it's so stiff that when this thing moves left and right, all three of these nodes are going to move by the same amount to the left and to the right. It's a diaphragm action. Not everybody knows what that means, but so what we would do in our model, if we want to capture that, is we would say, let's go ahead and put a diaphragm constraint into this. And so diaphragm, it's got a goofy spelling, and that would be a constraint. So what we would go in and do is we would come in and say, all right, I want the displacement in the x direction at that node to be equal to the x displacement at that node and equal to the x displacement at that node. And if we go to the next slide, then what that would say is that delta 4 is going to be equal to delta 7, and that's going to be equal to delta 13. And that is a constraint. And so what we're doing is we're defining relationships between degrees of freedom at different nodes. Okay. There are other constraints. That's a rather advanced topic, especially when you go to implement it in the matrix operations. It's very useful in building type structures. It's useful in bridges too. It makes the problem smaller. It makes it quicker to solve. It also gives us results that are more typical of what we would expect from a hand analysis. And so it's very useful but it's also very dangerous, right? Yeah, we'll think of a stupid analogy here. Microwave is very useful, but you got to be careful, because if you stick the aluminum foil in the microwave, you get bad things. Sparks tend to fly. So, right. Then the last thing that we'll talk about is a release. And a member release is something that's added to define the way an element is connected to a node. And so when we go in here, back to this, for example, maybe we would want to have one of these beams that are pinned to at its end instead of connected rigidly. So in that case, what you would do is you would come in with the purple marker and you would put a pin in there. And that pin, the word that we use to describe that is a release. We're releasing the connectivity between the moment at the right end of that member and the node that it's attached to. Or we would be releasing the moment connectivity between the top end of that column and the element that it's connected to as well. And so those three terms are important. We use them a lot, but we have to be careful when we use them, because if you say the wrong thing, then you get the wrong answer from your professor, and then nobody's happy, right? I've wasted my time describing the answer to the wrong question, and you're back to square one. All right, so let's talk about joint restraints. So this is an example of a joint restraint. We have a column coming into a footer. And so in this case, you might model that as a fixed support. I don't know, it depends on the thickness of the base plate and how it's all called out. You might actually model that as a pin support instead, where if it were modeled as a pin support, then you would model it like this. Even though there is still a rotational degree of freedom there, that would be a pin support instead of a fixed support. This guy isn't so ambiguous though. If we're modeling this, then we have a member coming down, we have a node there, and that node is probably going to be considered to be fixed. With 4 anchor rods on each side and all of that reinforcement, I don't think anybody would model that as a pinned column support. And then just to eliminate any doubt whatsoever, this is something that would certainly be modeled as a pin support. This just is begging to be modeled as a 3-dimensional structure. So let me draw a cube at the bottom instead of a, and so in this case here, you would have 6 degrees of freedom. We could sketch that in just with that, and that is rather crude, but everybody kind of understands what that means. So if we come in here, we would end up with a displacement delta in that direction, a displacement delta in that direction, a displacement in that direction as well. And then we would also have a vector that looks like that. So it's double-headed, which implies rotation, or we could put the rotation on it like that. We could have our rotation vector like that, or like that. I don't know why that erased. And then we can have our displacement vector like that. So right hand, and there we get that. So that would be theta, that would be theta. I've got this backwards. I took my freshman year, I took an entire physics exam using the left-hand rule. That's how. Yeah, that happens, right? We all make dumb mistakes. Some of us make more than others. I've come to believe that wisdom is simply the act of making lots of mistakes and learning from them. And so I'm no smarter than anybody else. I've just done everything wrong already. You guys haven't had the chance to screw enough things up yet. When you get older and you make more mistakes, then yeah, Joe's checking me on that, right? So here's my, I've got this other one backwards. That's why Joe.
Yeah, that one should be the other one.
Yep. So when I see you studying like that, I start to doubt myself. Right? All right. So anybody know where this column or where this base plate is by chance? Some of you may have been in that building. This is in the casino at New York Casino Resort in Las Vegas. And so the New York Resort has a roller coaster that runs around on the top of the building. And so it has these big roller coaster type columns that come down through the structure. And so this is one of those that's in an unfortunate place in the lobby, and everybody has to walk around this in order to get to the escalator, to the steps. So Occasionally somebody recognizes that, but not very often. You guys probably recognize this though, right? This is outside the rec center, right near Nippert Stadium. So that would be another example where that would be a fixed support. And for some reason, some of these light masts are actually grouted and others are not. So this one here that's near the elevator going up into the rec center classrooms is not grouted, but if you go across and look at one on the opposite side of the field, it is grouted. And I've asked a bunch of people why one would be grouted and the other one isn't. Nobody seems to know the answer to that, and I certainly don't either. Yeah, I don't have a good answer to that. Okay, here's some more columns. This is actually at Mercy Hospital in Fairfield. Funny story, child A was being born. Wife went into labor one afternoon. We went to the hospital. Turns out that giving birth takes a long time. So I got hungry. I went out for Chinese food and I rented some videos. The maternity ward was nice. They had like a TV, and at that case, it was like a VHS player, right? Because that was 2002. And so when I was out there, they were pouring these footers around. So I took some pictures of the columns when my wife was up in the hospital in labor. And so she's not my wife anymore. I'm not sure what happened, but I've got a different wife now. I'm not sure if this one episode contributed or not, but right. So in this case, these are rather light base plates. So I would probably model these as pin supports. Here's a bridge outside of Pittsburgh, Pennsylvania. And I stopped and took pictures of this one snowy day because here you can see these supports at the bottom. It's an inclined column with a pin support. And one of the things that I love about bridges is that they're not shy about hiding the structure, right? So they keep everything out where you can see it. And so you can see this is a true pin. And if we were to model this in 3 dimensions, this would be I didn't quite get that. This would be an interesting case because now you have a situation where you have 1 degree of freedom, 2 degrees of freedom rotationally that are restrained, but the 3rd degree of freedom is free. So you would have a degree of freedom coming out this way that is unrestrained, but you'd have a degree of freedom there that is restrained, and then you would have another degree of freedom that way that is restrained as well, rotationally speaking. So that's kind of interesting. So here's a bit of a discussion about member end releases. And so we'll go back to the building context in this case. And so we have 3 cases here. We have the case on the left where we have full restraint. If we're going to put our steel design hats on, that would be referred to as a fully restrained connection. And basically what we're doing is we're welding the shit out of the beam. We're going to go in and weld the flanges of the beam to the column. We're going to weld the web of the beam to the column. And the idea is that if the end of the beam rotates, then the column has to rotate by the same amount. The middle case is a simple connection. And typically what we would do is take this shear tab or single plate shear connection, and we would model that analytically as a pin. Yes, there's some moment that could be transmitted there. You're going to get maybe a little bit of a couple between this top bolt and this bottom bolt. But generally speaking, there's going to be a lot of rotation at the end of the beam relative to the face of the column. So we would model that as a simple connection with a major moment released. And then there's the case on the right where you have some transmission of moment. That would be a partially restrained connection. So when we go in and model these in our computer, we would model them like this. The first case where we have a fully restrained connection, we just have full connectivity. Well, I just drew a circle and that's not right. We have full connectivity between all of the elements that are framing in here. One other thing to note is that even though this might be one physical member that's passing through here, we break it at that location and model it as 2 analytical objects, right? And so when we have a beam that's simply connected to the column, we have to put a release in there to tell the program that there is no moment transferred between the end of that member and that node. Now, that's why we define them as, that's a good difference between a truss node that doesn't have a rotational degree of freedom and a frame node that does with a release, because here we want connectivity between these members that represent the column, but we don't want that rotational connectivity between the beam and the column. So that's why that goes a little bit further perhaps to answering your question, Joe. And then over here on the right, what we would do is come in and define some rotational spring stiffness. Maybe that would be something like there is a moment of 400 kip inches per radian that is developed. And so that would be a spring stiffness, but the units are a little bit awkward because it's a rotational spring instead of a translational spring. All right, and then so examples there. Here's a three-dimensional problem again. So if I were to sketch this in here, here's the blue doesn't show up so great. What color could I use? Let's use green instead. So here's a node, and I'll try and give it 3 dimensions like that. So we would have that node connected to these members coming in from the left and the right, right? So we have these flange plates that are giving us moment connectivity, so there's no release there. But for the member coming out, this guy is just connected with a seat connection, so I would go in and add a release between the member coming out here and that node. Okay, I should also mention that each one of these beams has a major axis and a minor axis moment, and we can release one and not the other. We can release the other and not the one, or we can release both of them. And when we go through and look at SAP 2000, each end of the beam has 6 degrees of freedom. There is axial force, shear in one direction, shear in the other direction. There is torsion, there is moment in one direction, moment in the other direction. So there's 6 degrees of freedom, 6 end actions at every end of it. And we can release any one of those 6 end actions at either end of the member. So a total of 12 releases that are associated with each member if we do a 3-dimensional model. Here's another case. Anybody recognize this? Again, I'm probably reaching a little bit. This is at the Washington National Airport, Reagan Airport in Washington, D.C. And just FYI, if you go into an airport in the nation's capital and start taking pictures of the structure, particularly in the years that followed the the September 11th attacks, so you get a lot of attention really quick. So you have to either be really discreet or be ready to show your ID and have a very nice explanation as to why you look like you're about to facilitate a terrorist attack. Anyways, this is a pretty cool structure. If we take green won't work in this case. Let me go to purple. So if we take a section here, this is actually a flange cruciform column. So in section, it looks like that, and then it has a pipe in the middle. So it's a member that's a pain to build up, but it works really great because it has similar stiffnesses for flexure around about both axes. And then so we're framing in from one direction with this beam that's continuous across there. And so there's, and then we have this beam coming in from this direction as well. So this would be one great big node, and there's no releases whatsoever there. This is a parking garage in Philadelphia. I took my kids to, no, it's in Boston. I took my kids to Boston for a conference, and we did the Tea Party cruise and all that other stuff. And then they're like, Daddy, why are you taking pictures of the parking garage? Like, because I'm an engineer. That's what engineers do. My wife also asked me that same question, by the way. And so here's a case where we would have a moment release for that member there. This is going to give us a moment release for that member there. There's going to be a member framing in from the right, and assuming that it's also connected with just a web angle, it's going to have a release there as well. And so when we come in with the column, the only real connectivity here is with the member that's framing continuously through there with that column. Okay, so we have 1, 2, 3 releases for strong axis moment. If we're going to dot our I's and cross our T's, we'd probably release torsion there as well, and maybe even weak axis moment. Okay, here's some other examples. This is Krempa Federal Credit Union. They put up a new building off of Union Center a few years ago. So I went over there every couple of weekends and took pictures while they were putting it up. And what's interesting here is you can look at these intermediate filler beams, and these intermediate filler beams would be released there as well. So you have one beam connected to another beam, but there's a moment release between the joist and the girder in that case. And so these particular pins tend to look like this when we draw a schematic. So here's a beam or a girder with a pin in it. We think that this is purely a means of imposing sadistic pleasure on students in structural analysis, but it's not. It has a real application. This is a bridge over 275. This is Hamilton Avenue over 275. When I leave home and go to campus, this is one of a couple of ways I could go. And so this particular bridge has a pin in it. And if we want to model this bridge the way that we think it's going to behave, we would put a pin in our model. That begs the question, why would we put a pin in the bridge like that? And the answer to that question is that before computers, BC, doing the analysis was cumbersome. And if it were a indeterminate structure, it's even more cumbersome. So you remember that conversation from your undergraduate analysis class where you calculate the number of degrees of freedom or the number of degrees of redundancy in the structure or whatever. And anyways, if you can add a couple of pins to a bridge, it takes a bridge that would otherwise be indeterminate and makes it determinate. So then you can do the analysis by hand and get results that should be quote unquote exact. Right. Those are the word, it's one of those words I hate to use, the word exact, the word accurate, the words I do. Those are all words that I hate to use, but, occasionally you have to. So that's why we have pins. And since we have those pins, it's important to know how to model them. So if we were going to create an analytical model of that girder, it might look like this, right? It's probably one physical member going from point B to point E, but we have to break it up into two analytical objects because we have to have a node there at the restraint. We have another analytical object over here, and then at this node, what we're going to do is we are going to release the left end of member BC, and that provides a moment release between member AB and member BC. That's not the only way of doing it. We could also model it like this, where we put that moment release at the right end of member AB. That also provides a moment release between member AB and member BC. That would also work. That would be just fine. It's an apples, tomato kind of a thing, right? If Joe does it, it ends up one way. If I do it, it ends up the other way. If I do it today, it ends up one way. If I do it in 3 weeks, I do it the other way. It doesn't really matter. What you can't do, what will not work, is putting a release on both sides of the node. And if you put a release at the right end of the first member and the left end of the second member, then what you're saying is that there is no moment connectivity to that joint at all, and that joint is free to spin in your analytical model. And that is a rigid body motion. And that rigid body motion results in a singularity in the solution of the problem. So we go back to this case where we had the matrix ops K times delta is equal to the loads P. If you put a pin on both sides of that node, and if that node is free to rotate without any stiffness attached to it, then the stiffness matrix becomes singular. It has a zero determinant, and that is linear algebra speak for thou shalt not go there, right? So that represents a structural instability. Now, looking at the, I'm pointing with my finger, looking at this guy down here and looking at this guy up there, it looks the same to us. If you were to show it from one engineer to another, they would certainly know what you mean. But when you translate it into analytical linear algebra, it makes a big difference. So you can either put the release to the left of the node, to the right of the node, but you can't put it in both places. If there were another member framing in, maybe there was a column in here in a building, then it would be okay, because then that node would be connected to that column member, and the column would keep the node from spinning. But there isn't a column there because this is a bridge application instead. All right, so in summary, we have these degrees of freedom for these different types of models: plane truss, plane frame, space truss, space frame. And then I've included the member actions here as well. For a plane truss, we just have an axial force in each member. For a space truss, we just have an axial force in each member. For a plane frame, we have axial force, we have shear about one axis and moment about the other axis. And then for a space frame, we have axial force, shear in 2 directions, moment in 2 directions, and torsion. Now, I mentioned directional cosines earlier. This is the definition of a directional cosine. And these directional cosines become important when we develop the analytical model behind the scenes, when we develop the stiffness matrix and we go ahead and solve that system of equations. So one of the things that I've asked you to do in the first homework is calculate directional cosines for the members that are in the truss for that assignment. Those are provided here for you. Inevitably, I'll get the question, well, where are the directional cosine equations? They're right here in lecture M01, slide 52. All right, and then later in the semester, we'll start talking about continuum elements as opposed to discrete elements. We use them a little bit in CAE structures. Usually we use shell elements because they're good for modeling floor slabs and bridge decks and shear walls. And those objects are shown here. In SAP 2000, they would be called area objects. We can call them finite elements as well. And so each one of these connects to either 3 or 4 nodes. We have a triangle element that connects to 3 nodes. We have a quadrilateral element that connects to 4 nodes. And each one of these has degrees of freedom as well. Let me go ahead and sketch those in. Whoops, that's not what I meant to do. Let me sketch those in for this guy over here on the right. So over here at, say, node J1, we would have a displacement in that direction. So that's displacement 1. Let's say that that's X. Let's say that that's Y. Does that work? Yes. And then this is going to be Z. So that would be a displacement X. That would be a displacement Y. And then what we would have is a translation Z, delta Z like that. And then what we would have is also the associated rotations. So we would have a theta here, theta Y. I'm using the right hand because Joe caught me cheating last time. That would be theta about the x-axis. And there's often not a theta Z, but sometimes there is. Sometimes you have this theta Z, which looks like this. And sometimes it's there, sometimes it's not. Sometimes you have 6 degrees of freedom in every node. Sometimes you only have 5, because that theta Z is called a drilling degree of freedom because it symbolizes a drill bit going through the slab. And that drilling degree of freedom isn't all that useful. So some formulations include it, some formulations leave it out. And then the last object is a true 3-dimensional quadrilateral. And in this case, we often don't have rotational degrees of freedom. In this case, we usually just end up with 3 translational degrees of freedom. And if you want to account for the case where you have some rotation, then that's usually accommodated with 2 different translations acting over a displacement. So if you have a displacement in those 2 different nodes, then relatively speaking, that represents a rotation between those nodes. All right, so that brings us to the end of the hour. I didn't get back to visual analysis at all, so we'll start there next time. At the end of the presentation that I posted for today are the steps for creating an FE model. Maybe before Tuesday, you could look through those tutorials. Maybe you want to start tinkering a little bit. If you just look at it and kind of get a feel for what to expect, that's probably enough. And what you could do is go through here, and here's basically the steps we would have. So I'll start with this on Tuesday, and then we'll work through those tutorials and actually get some experience with visual analysis in SAP 2000. All right, so with that, I'll hang around for a few minutes and answer questions you might have. Otherwise, I'll see you either in office hours that I'll post over the weekend or in class on Tuesday at 12:30.
Sponsor, I got a quick question here. I'm in the computer lab.